In this lecture, we will introduce the notion of logarithms. In the last lecture, we mentioned that the binary search algorithm takes O of log n time, and that it's a more efficient algorithm compared to sequential search. Here we're going to actually show that. So if we want to actually understand how effective binary search is, well, we're going to have to do a little bit of math. And what I mean by a little bit, I mean a good amount. Okay, we're going to do a lot of math. Now, specifically, we're going to take a look at logarithms and see how, let me say interesting. It's a very interesting concept when we see what happens with logarithms. So if we remember in our number guessing game, we saw that if we had to pick a number between 1 and 100, we needed only 7 guesses to pick that actual number. But what about other ranges? Well, let's take a look at this table here that shows us different ranges and how many comparisons we would need. So if we needed to pick a number between 1 and 10, we only needed 4 comparisons. 1 to 100 we already said is 7. If we had to pick a number between 1 and 1,000, we would need 10 comparisons. If we had up to 10,000, we would need 14 comparisons, and so forth. So notice that if we go all the way up to a billion, if I told you pick a random number between 1 and 1 billion, and then we use the binary search approach for determining what that number is, we only need 30 comparisons over here. I mean, look at this. 30 comparisons is all it's needed to correctly guess a number between 1 and 1 billion. That is huge. Are you convinced that this is a huge deal? Well, if not, let me put things in another perspective. Let's suppose you were to search 1 billion elements. Okay? And so here we're comparing sequential search to binary search here. And let's suppose it takes 1 second to compare an element. It would take 31.69 years to compare all 1 billion elements. Okay? I think most of you have not even been around for 31.69 years. So this is a very long time if you did 1 comparison per second. What about binary search? It would take 30 seconds to do the search. Okay? 30 seconds for binary search, 31.69 years for sequential search. That is a huge difference. So how does this work? I mean, why do we have just so few comparisons when we have these very large ranges? Well, the number of comparisons that we get depends on how many divisions we can make until we can't do any dividing any further. Because remember, the way this works is we're taking some set of numbers or elements and we keep cutting it in half. So how many times can we do this? And that's what we're finding here. For even very large numbers, when we keep cutting in half, we're cutting down a drastic number of elements initially. So that's how we're getting those numbers. So here's an interesting question. So let's say we're given a specific number of steps and a specific number of divisions, which we're going to denote as S. If we're given that, what is the exact range that can be searched in S steps? Here's a table that answers that question up to 10 steps. So if we have 0 steps, well, the only possible range is just that there's one thing. There's no comparison. In 1 step, we would see that we can have up to 2 things in there. If we had 2 steps, our range can be 4, and so forth. And we also, this is a big observation, is we wrote the range as a power of 2 as well, just to show that there is this correlation between the number of steps and the range of values that we can actually search. So just to give an example, let's say we go back to a range of 100 elements. We would see that 6 steps is not enough because we can only search up to 64 items in order to find something. So we would actually have to go to 7 steps to be able to handle it. In fact, we can actually go up to 128 items in order to do 7 comparisons. What's interesting is that doubling the range each time actually creates this series of numbers. And this series of numbers is the same as raising 2 to some power. So we can express this as a formula. So if S is the number of steps and let's say r is the range, then our formula is that r equals 2 power s. So in other words, if we know the number of steps, if we know the value of s, then we know the range by taking 2 and raising it to the number of steps power. However, our original problem was the exact opposite. So here, if we're given the range, what is the number of steps? So we have to compute the inverse of raising a number to some power. And this inverse is what we call a logarithm. So let me give you the formula for this. So if s is the number of steps and r is the range, if we're given the range, then log base 2 of r is going to give us s, or give us the number of steps. So in other words, we're just saying that the number of steps is equal to the logarithm to the base 2 of our range. Now, why are we doing log base 2 and not something like log base 3 or log base 10? Well, the base 2 logarithm of a number is just simply the number of times we have to multiply 2 by itself to get r. So let me give you an example. Log base 2 of 16 is 4. This is saying in order to get 16, I have to multiply 2 with itself 4 times. So 2 times 2 times 2 times 2. If I were to use some other base like log base 3, I would be multiplying 3 by itself so many times to get some number. But here, we're just saying that we would have to multiply 2 by itself several times to get some number. Now the question you should be asking is, how do we actually calculate log base 2? Because if you go on a typical calculator, it only computes log base 10. Well, there is a simple trick we can use. We can actually convert to base 2 by multiplying by 3.322. So in other words, we would calculate log base 10 of some number, and then multiply it by 3.322, and that will help us with getting the log base 2 value. So let's look at an example here. So let's say we want to get log base 2 of 100. Well, what we can do is compute log base 10 of 100, and that would give us 2, because 10 squared is 100, and then we multiply that by 3.322. So if we multiply that, we get 6.644. Now that's close to 7, so the last step is just that we would round up to the next whole number. So in this case, we take 6.644, we round it up to the next whole number, that gives us 7, and sure enough, log base 2 of 100 is 7. The whole point of all this, the main observation I want you to get out of this, is that as the range grows, the number of steps needed doesn't grow anywhere near as much as the actual range. Because we saw when we went up to 1 billion, we only needed 30 comparisons. If we went with substantially larger numbers than a billion, the number of comparisons would still be pretty small. And this is because logarithms do not grow anywhere near as fast. They do grow, but they don't grow as quickly as you would think. So it's a very slow growing function. So as we increase the value of the range, the number of steps does grow, but nowhere near as much.